Good evening, Titans. This is Mr. Simpson, and we're going to begin Chapter 5 tonight. This is Lesson 5.1, Solving Systems of Linear Equations by Graphing. The essential question is, how can you solve a system of linear equations? Now, what you will learn through this video is you'll learn how to check solutions of systems of linear equations. You'll learn how to solve systems of linear equations by graphing, and also use systems of linear equations to solve real-life problems. Now, if you open your journal book, there are a couple of vocabulary words here we need to define. So first, the system of a linear equation is a set of two or more linear equations in the same variables. And so if you look, both these lines here are linear equations. Okay? They're both linear equations in two variables. This is called a system. Obviously, they each draw a line, and unless these lines are parallel, they will intersect. And usually that's what we're looking for, is to see where they intersect. Now, a solution of a system of linear equations in two variables is an ordered pair that is a solution to each of the equation in the system. So what we're looking for is this point that makes this line true and makes this line true, or that equation true. So the first thing we need to be able to do is determine, is an ordered pair a solution to the system? And to do this, we must plug it into each equation and see if it makes it true. So if we plug, again, remember it's always x followed by the y. So we go 2 plus 5 equals 7. Well, 7 equals 7. That checks for the first equation. Now we're going to plug it into the second one. So it's 2 times 2 minus 3 times 5 is supposed to equal a negative 11. Well, 2 times 2 is 4. Minus 3 times 5 is 15. Keep change. That's a negative 11 equals negative 11. That checks. Since this ordered pair makes both equations true, this is a solution. So now let's check letter B. So again, here, this is the x, this is the y. So I plug 0 equals negative 2 times negative 2 minus 4. Negative 2 times negative 2 is a positive 4, minus 4 is 0, and 0 equals 0. So that checks. Now I'll plug it into the other one. 0 is equal to a negative 2 plus 4. 0 is equal to, well, negative 2 plus 4 is 2. This is not true, so then this is not a solution. Not a solution. So if we look at a couple more examples here, if you want to pause this and try these, you can, but I'm going to go ahead and work these right away. So again, we substitute the x and the y in for each equation. So 2 times 1 plus negative 2 has to equal 0. Well, 2 times 1 is 2, plus negative 2 is 0. 0 equals 0. That checks. So now I plug it into the next one. The opposite of x, which is 1, plus 2 times negative 2 is supposed to equal 5. Well, negative 1 plus negative 4, and that's a negative 5, does not equal 5. So that does not work, so this is not a solution. So now we'll test the next one. Again, x followed by the y. So 4 is equal to 3 times 1 plus 1. 3 times 1 is 3, plus 1 is 4. 4 equals 4, and that checks. So now we plug into the next one. So 4 in for the y equals the opposite of 1 plus 5. Negative 1 plus 5 is 4. 4 is equal to 4, and that checks. So that is a solution. So again, a solution to a system of linear equations must make both equations true at the same time. Now, the core concept here is we really want to be able to solve a system of linear equations by graphing. So the steps that we're going to use is to first graph each equation on the same coordinate plane. We'll estimate the point of intersection. And then we're going to check the point from step 2 by substituting for x and y in the equation of the original system. So here we go. This first one has a we're going to graph each of these using slope-intercept methods. So y-intercept of 5 here, and then it goes down 2 over 1, down 2 over 1. So again, it's kind of hard to graph this on the iPad here, and then this one has a y-intercept of a -1, but then it goes up 1, 2, 3, 4 over 1. And so it appears that they intersect right there, which is the point 1, 3. So then we have to check. So 3 is equal to a -2 times 1 plus 5. -2 plus 5 is 3. 3 is equal to 3, and that checks. Now I plug it into the next one. So I have 3 is equal to 4 times 1 minus 1. 3 is equal to 4 minus 1. 3 is equal to 3, and it checks. So yes, the solution to this system, or where these two lines intersect, is at the point 1, 3. So again, here's just a couple more examples. So this first one has a y-intercept of 3, and then it goes up 1 over 2, up 1 over 2. This one has a y-intercept of a -5 and goes down 3, right 2, or remember I can go up 3, left 2, then up 3, left 2. And as you can see, again, we're going to find a point of intersection right there of -4, 1. And then we should check it. So if we check this, again, we have 1 is equal to 1/2 times a -4 plus 3. Well, half of a -4 is -2 plus 3 is 1. 1 equals 1, and that checks. Now I plug into the next one. So again, I have 1 is supposed to equal to -3 halves times a -4 minus 5. Well, again, two negatives make a positive. This 2 divides with this 4 to make that 2. 3 times 2 is 6, and 6 minus 5 is 1, and 1 is equal to 1, and that checks. So there's the solution to that system of equations by graphing. Now, if we take a look at the last example here, because these are given to us in standard form, I could graph them by using x and y intercepts, or I could put them in slope-intercept form. And I'm going to put it in slope-intercept form. Y is equal to a -2x plus 5. And then here I'm going to move that over, so that gives me -2y equals -3x plus 4. And now I'm going to divide both sides, or every term, by a -2. That gives me y is equal to a positive 3/2 times x minus 2. And now I'm going to graph. Y-intercept of 5 up here, and then down 2 over 1, down 2 over 1, down 2 over 1. Okay? We draw our line through those points. Then we have a y-intercept of a -2. I go up 3 over 2, and as you can see, it intersects right there at that point of 2, 1. And then we should check. And again, I'm going to check into the original. So I have 2 times 2 plus 1 is has to equal 5. 4 plus 1 is 5, and 5 equals 5, so that checks. Now I'm going to plug it into the next one. So 3 times 2 minus 2 times 1 has to equal 4. That's 6 minus 2 is 4, and 4 is equal to 4, and that checks. So we've determined that 2, 1 is the solution to that system. All right. Now, here's an application problem. And again, it says for the first tour on Monday, a museum sells 4 child tickets and 8 adult tickets for $128. For the second tour, the museum sells 6 adult tickets for $72. Find the price of 1 child ticket and the price of 1 adult ticket. So we set this up. We have 4 times the price of a child ticket plus 8 times the price of the adult ticket equals $128. The second scenario is we had 0 child tickets plus 6 times the adult ticket price is equal to 72. Well, if we let x equal the child ticket price and y equal the adult ticket price, we set up this system now. 4x plus 8y equals 128, and 6y equals 72. If I solve each of these for y, I now have them in slope-intercept form, and this should be a -1/2 x there. And now I graph. So my graph, my first line, the black line, I have a y-intercept of 16. I went down 1 over 2. This one was just a y, so it's a horizontal line. So then they intersect right here. And if you look at where they intersect, looks like that's 8 on the x-axis, which is 8 children tickets. Or actually not 8 children's tickets, it's $8 for a child ticket, sorry. And then the price of an adult ticket, which is on the y, is $12. So it's $12 for an adult ticket and $8 for the child. Okay, so there's how we can use the system of equations to solve a practical problem. We're going to skip this next, and so we have enough to be able to do the student journal problems on page 135. So try to do 1, 3, 7, and 10 in your student journal, and we'll discuss these tomorrow in class. Have a great evening, Titans.